Okay, we're live. Today we're going to be talking about generalized linear regression models, again using RStanArm. So this is a generalization on the sorts of things that we were doing on Tuesday, attempt to move beyond. But before we can go forward, we have to go back to the fact. It's Columbia. Columbia's got rules. I try to barely stay within the rules, and that means I have to disclose the fact that using Stan outside of Columbia creates the appearance of a conflict of interest. Okay, so there's this data set talked about in the reading about an experiment they did to trap roaches in roach-infested buildings in New York, such as the International Affairs Building. I don't know if IAB was actually part of the study, but I don't think they had difficulty finding buildings. So there's going to be, let's just look at that. All right, so this is a bit more of a complicated depiction, or it's a depiction of a more complicated prior predictive distribution for the data determining process thought to be at issue with this. So the ultimate outcome is not actually the number of roaches, it's the number of roaches caught in the roach motels under the experiment. And so that is going to be an observable variable. We have as another observable variable the number of roaches that they observed before the experiment in those buildings. The treatment, some sort of food or whatever that they put out to catch the roaches. I'm not even sure what that is. Senior is if the building is only for old people. So I guess IAB probably was not, well, it could have been 0 on that variable. Anyway, and then offset, we'll talk about. That has to do with the number of days in which the treatment was operational, and that affects things as well. So all of these variables with their corresponding coefficients go into the so-called linear predictor, eta. And everything in this box here means that this happens for each observation. The things that are outside the box, the parameters and whatnot, and also the stuff that goes into priors, it needs to be accounted for once. But there's only one alpha, not a separate alpha for each of the observations. So the way in which these particular plots are plotted, and I think this is pretty common, is to put a box around things that sort of indicates repetition or a loop for all the observations that you have. And so this, the previous number of roaches, the treatment variable, whether it's a senior building, those each have a respective coefficient. Those get all added together along with an intercept to create the linear predictor eta, which is a deterministic function of all those things. And in a generalized linear model, it's going to be a linear function of the parameters. Now, as we go along, hopefully you'll get a better appreciation for the fact that there's no reason why you're restricted to a linear model. But those are the sorts of things that you see more often in the frequentist literature. Those are the sorts of things talked about in the reading. But it's worth dwelling on the fact that the fact that you see so many linear or generalized linear models. So generalized linear model means that eta is a linear function of the parameters, but there can be a nonlinear transformation relating eta to the expectation of the outcome. In this case, the outcome is going to have a Poisson distribution, and so the parameter of the Poisson distribution is mu. That has to be positive. In general, a linear function of all this stuff is just going to be any real number. And so the most common thing in Poisson models is to exp eta and assign that to mu in order to have an expectation for the Poisson likelihood that is guaranteed to be positive. So you'll see a lot of generalized linear models out there in the literature, but it's good to reflect on the fact, why is the linear form, connecting the outcome, the predictors and the coefficients to the linear predictor eta, so common in the frequentist literature. So you will hardly ever see nonlinear model. You might see some interaction terms, but that's still linear with respect to the parameters. What are some of the reasons why in the frequentist literature these linear specifications are so common?
Can perform a lot of monotonic transformations to linear RST models, such as take logarithms of everything, which is what economists do.
Yeah, that's part of it. Have transformations to the predictors in order to make a linear model more plausible, and that's helpful. But why would they be seeking to estimate a linear model in the first place?
Yes, if you wanted to simulate for a very large number, then if it's linear, then it will always be going in the same direction. Whereas if you have polynomials, then strange things could happen to your predictions.
That is certainly part of it, in that you wouldn't have a polynomial relationship between past number of roaches and the linear predictor. And as long as this is a monotonic transformation from mu, the linear predictor, to mu, the expectation, then yeah, nothing too crazy could happen with your model, as opposed to if this was tangent or something relating the past number of roaches to eta or some other periodic function. Other reasons?
If we have a dichotomous treatment, it's equivalent to doing a difference in means.
That is true. So this is a binary variable, and so is the senior one. This is just a count. So a lot of it goes back to the goals of frequentist inference. So let's say you had cosine of lag roaches or something like that going into eta. There would no longer be sort of a single effect of lag roaches. There would be different effects depending on where you are in the cosine curve. So how would you test the null hypothesis that the effect of lag roaches on future roaches is 0, if the effect is actually the period of effects from 0 to 2 pi? That's part of it. So if there's no longer a single effect, then you can't really say, test the null hypothesis that this is 0 over the whole period. In addition, it's more difficult to derive the sampling distribution of a test statistic in a nonlinear model. Oftentimes, asymptotically, you can come up with something, but certainly to get good finite sample behavior of the test statistic, it helps to be estimating a much simpler model, maybe one that is too simple for the data generating process you're considering. Yeah.
So because frequentist statistics doesn't really rely on computing power. So if you want to like evaluate something by hand, it has to be integrable. And if you had some polynomial or some like trigonometric functions, they would not have like simple antiderivatives.
Possibly true. Right. You know, with modern computers these days, you can usually do simulations as to what the sampling distribution of some test statistic will be in your data set or a data set of your size without having to do analytical integrals. So frequentists can use simulations as well. A lot of people who want to use frequentist methods don't want to. And so one of the things that really aggravates Bayesians about the frequentist literature is that there's all these people that say, oh, well, the frequentist approach is so much simpler, it runs so much faster, etc. And that is, insofar as that is true, that's because there's another, convention that frequentists have established for themselves, that if something has an asymptotic justification as n goes to infinity, then you're allowed to use it irrespective of what n is. You're not required, and so if you're trying to figure out the sampling distribution of something for finite n, that is going to depend on the data generating process. That's going to depend on the true values of beta and alpha and whatever else you've got going on. This whole what if n goes to infinity basically means that you don't have to worry about the nuances of the data generating process because you basically have the population. But if you're doing this for finite n, then the data generating process matters as far as how that affects the sampling distribution of statistics. So if journals or whatever required everyone who submits a paper that uses a finite data set to really figure out what is the distribution of the test statistic they're using to reject their null hypothesis or whatever for a wide range of plausible values of the coefficients and the other parameters, and the simulations you do from a frequentist perspective are conditional on the parameters, you would have to run like billions of simulations for all different combinations of the parameters in order to establish that the test statistic that you're going to use has some sort of reasonably known behavior for the size of a sample that you ostensibly took from the population. But you're not required to do that if you're a frequentist. As long as like this could work for infinite data, then you can use it. And so with the Bayesian approach, we're conditioning only on the data that we have, but we have to do MCMC and whatnot, and so that's perceived as taking a long time. In addition, using a linear predictor, making eta be a linear function of the parameters, makes it much easier to solve the optimization problem to find the values of the parameters that yield the mode of the likelihood. If you had nonlinear functions going on here, could be multiple local optima, saddle points, all kinds of other things that are more difficult to deal with. Now with Stan, or with MCMC, particularly in Stan, we're not going to the mode and stopping. We're not doing optimization at all. And so we're never going to exactly land on a local optimum or a saddle point. We're just going around the whole posterior distribution using the physics analogy. And so a lot in more complicated models, if you were to do it from a frequentist perspective, you'd have to worry about problems due to the optimization algorithm. And with Stan, you're certainly not going to have those problems. You might have fewer problems, you might have different problems, and we'll talk about how to deal with the problems that you might have, but you won't have saddle point problems. So that's another, to avoid those, that's another reason why these, from a frequentist perspective, are usually kept pretty simple. So Remember that in a generalized linear model, eta is what is a linear function of, stuff. There's a nonlinear relationship relating eta to the conditional expectation mu. So this is similar-ish to the diamond price thing that we were doing on Tuesday, where we took the log of the outcome, and technically our coefficients and whatnot pertain to the expected change for a 1-unit change in a predictor on the log of the price of diamond. But we didn't really ultimately care about the logarithm of price of diamond. We wanted to assess the sensitivity to carats or whatever in dollar price. So the coefficients, even the posterior medians that we got, didn't directly answer us that question. But again, these coefficients are sort of related to the log expectation of the number of roaches caught. So here I've illustrated this with normal priors, independent normal priors. That is what is the default in RStanArm. Presumably by this point you could also think about those being generated by inverse CDF transformation of something, but we don't have that in RStanArm just yet. So if we were to think in terms of normal priors on alpha and beta 1, beta 2, beta 3, let's say beta 1 applies to the previous number of roaches, beta 2 applies to the treatment variable, and beta 3 applies to whether it's a senior building or not. What might be some reasonable choices for the prior means and prior standard deviations of our coefficients and our intercept?
So what is alpha again? Alpha is the live roaches.
Alpha is the intercept going into the linear predictor. Beta 1, let's suppose, is the coefficient on the previous number of roaches.
So can you explain what mu is? So mu is we hold like every predictor to his like mean values. I mean exponential mean values to have like a baseline, and then we make variations like above or like below the mean.
Right. So eta mu n is simply equal to e to the eta n, and then eta n is equal to alpha plus beta 1 times lag. That's a plus beta 2 times treatment plus beta 3 times senior. All right. So this everything in the square here is indexed by n. In general, any two buildings, they don't have to be the same. So they're going to have different numbers of previous roaches. Some are treatment, some are control, and then some buildings are senior buildings, others are not. So we want to take each of our predictor values, multiply it by the corresponding slope, add those all together along with the overall intercept. We get some value of eta, which is going to be like any real number. And then we apply the transformation eta to that in order to get a strictly positive conditional expectation for the count of the number of roaches trapped. So who has thoughts about priors?
Well, for the intercept, you can't really go below 0 because you can't have negative roaches, I guess.
That's true. You cannot have negative roaches. However, you can have negative eta. So if eta was like negative 2, e to the negative 2 would still be a positive number. So particularly, let's put alpha aside for a second because that's one of the more difficult ones to think about. Let's say beta 1, the coefficient on the previous number of roaches. What might we think about that before we see the data?
Something positive.
Positive.
And
So
like thousands.
okay, so remember, I kind of, this was not the greatest. This is number of roaches trapped. This is the number of roaches observed before the experiment. So it does make sense that this should be positive. assuming the treatment has any effect. The more roaches there are, the more you would anticipate to trap. But even if the treatment has no effect, really, the more roaches there are, the more might accidentally wander into the trap. So those are the things. So I do think positive. Good here. It is kind of difficult to think about what would be a reasonable prior standard deviation for something like this, in part because it's on log expected roaches caught. Okay, treatment variable, which is going to have a slope of beta 2. When doing an experiment, whether you think it or not, you're almost always going to center the coefficient on the treatment effect at being 0. In particular, because experimental people are suspicious of the Bayesian approach anyway. And so to say, well, I think my treatment is going to have a positive effect, you might think that, but in the literature, you almost always see the important coefficients having a center of 0 under the prior, which allows for the possibility that maybe the treatment creates more roaches or something like that, even if that doesn't really make sense. And then the coefficient on, is this a senior building? What might we think about that?
Is this Boolean, like yes or no?
Yes, it's a dummy variable.
Okay. So it could be 0, like if it's no.
Right. If it's not a senior building, then it's just coded as 0. But in terms of prior on the coefficient of it, you think it's positive?
I think there are more non-senior buildings in New York, are there?
My guess is, yeah. I don't even really know what a senior building is. I mean, it might be like an assisted living place.
Right. So even in general, there are fewer of those in a town than regular buildings.
I mean, does not senior though like pertain to whether the building, like seniority of the building, like how old it is? That would be
I think it's how old the people are.
That's weird.
So I think it means like assisted living place.
Okay.
So yes, there's probably not that many of them.
Yeah.
But our prior is not on like how prevalent this is. Our prior is on the coefficient on, let's just call this assisted living places. So do we think assisted living places are likely to trap more or fewer roaches than a regular building? And why is that?
Usually those are poor places with low maintenance.
People clean less often?
They have staff, usually. Maybe they have more rules for cleaning.
Would our like prior ideas about the number of senior buildings affect though our prior about the standard deviation of that coefficient?
So we're assuming a constant standard deviation for each senior building, irrespective of how many there are.
Okay.
So that may or may not be a reasonable assumption, but that's what RStanArm is capable of doing. Okay. So what's going on with all this on the right side here? Oh, and maybe I should explain more the offset. So the offset is constrained to have a coefficient of 1. And so it just goes in deterministically into the linear predictor. You'll often see these in models where the outcome is a count if it pertains in some sense to the number of opportunities for the count to happen. In this case, it has something to do with how many days the treatment was applied. So I'm not even sure that it totally makes sense. But I wanted to illustrate how to do an offset in a count model. Okay, so the rest of it, we have this other parameter lambda, and there's one of those per building. And so this is where it already starts to get weird if you're thinking of this as a frequentist perspective. How could you estimate as many parameters as you have data points? but that's only a problem if you're optimizing, or it's only a like devastating problem if you're optimizing. If you're doing the MCMC thing, we're just going to get a joint posterior distribution of everything. You might not be able to update your beliefs about these lambdas very much, but it's fine that they're there. Then the logarithm of lambda is going to go into the linear predictor along with everything else. And so this is kind of like the error term in a Poisson model. It comes in multiplicatively rather than additively, or like we take the logarithm of and add it and then exp it. So it actually has a multiplicative effect on the variance relating to the number of roaches caught. Anyway, the traditional prior on those is gamma with an expectation of 1. And the reason to use a gamma, or think about using a gamma prior for that is, we briefly had an example with conjugacy between the Poisson likelihood and the gamma prior a couple of weeks ago. So what you can actually do is integrate out lambda from the model when you go to estimate it. So the reason why we introduce this is to induce extra variability in the outcome that may not be accounted for by our predictors. And then we integrate it out in order to make the process easier. So like I said, this pertains to your prior predictive distribution, if you were just simulating the outcome. When we go to actually estimate a model like this, it's easier if we integrate out the lambdas. That way we have fewer parameters to worry about. And we don't really care about the lambdas anyway, because they're more or less just the extra noise term. Anyway, when we integrate lambda out of this system, what we're left is with a marginal distribution for the number of roaches caught as negative binomial rather than Poisson. And the negative binomial has the same expectation as in a Poisson regression model, but it has more variance, or at least as much variance, as in a Poisson. If you remember back when we were talking about discrete random variables, we found that the variance of the Poisson was equal to the mean, which is usually not good for social science. Most of the counts that we observe in social science have more conditional variance than the conditional expectation. And the negative binomial is one of the ways in which you can address that, because it has an extra parameter, phi, that goes into the gamma prior on lambda. And depending on whether that is large or small, you get less or more over dispersion relative to the Poisson case. So in the gamma prior on lambda, even though lambda will ultimately get integrated out, this gamma distribution is going to have an expectation of 1, meaning the shape and the rates parameter are equal, and they're going to both be equal to phi in this case. That has to be a positive value. So in RStanArm, the default for that is an exponential prior on phi. This is another one of those things where it's kind of hard to think about what would be, a reasonable value for the rate, or the expectation rate being 1 over the expectation in an exponential distribution for that, although the default value that RStanArm is going to use is oftentimes fine for that. Okay, so did we account for more or less everything going on here? Question.
We did, but could you explain please again what the offset was? Because it seems to me that the phi and the lambda, so that's kind of like the error parameter. Yeah. So what was the offset again?
Offset on models usually has something to do with the number of opportunities for whatever the outcome is. In this case, the offset is like the number of days that the treatment was in effect, or something like that. The number of opportunities. So anyway, it comes into eta with a coefficient of 1 that's not estimated. Or you could give it as coefficient and estimate it, but they talk about offset in the reading. So I wanted to give an example of that. Okay. So when we go to estimate this, I actually put an interaction in between the past number of roaches divided by 100 in order to get the units sort of reasonable, thinking that the more roaches there were in the past, the more in gross terms the treatment might look. I use just the default normal priors in RStanArm, which by default is going to have a mean of 0 and a standard deviation of 2.5 for standardized predictors. So you don't have to do anything special with your predictors. They're going to be centered internally, and the prior is scaled up depending on what the standard deviations of the priors are. And what the predictors are. Anyway, so the default prior for this is basically normal with a standard deviation of 0 and a scale of 2.5 interpreted in standardized units. So basically giving 95% probability that changing any of these predictors by 1 standard deviation is going to yield less than a 5 standard deviation change in eta. That's the way you could think about that. Okay, but I certainly probably could have gone in and put in at least a more reasonable prior on beta 1 under the presumption that it's going to be positive. So I specify family equal neg underscore binomial underscore 2. The negative binomial has like 9 different parameterizations. Anyway, the second one is the one that you want for a regression model, parameterized in terms of an expectation and an over dispersion parameter. Specify my offset is the logarithm of exposure to, that has to do with the number of opportunities, the days in which the treatment was in effect. And if you're going to just use the default like weakly informative normal priors, it is usually a good idea to specify the argument QR equal true. Has to do with a QR decomposition that I'm not really going to get into until we've talked about matrix algebra, but that will usually get better mixing. So if you kind of like don't care that much about your priors on the coefficients and the intercept, or the coefficients specifically, and you're just going to use like the same weakly informative normal 0 standard deviation whatever for all of them, you might as well try to give yourself a little bit of advantage in terms of the faster mixing. You'll tend to get a better effective sample size, tend to get fewer warnings. The sampling will tend to have better mixing, more efficiency, etc. Question about something?
About the distribution we're using, like, could you summarize what is the distribution of the prior of the likelihood and what are we going to expect for the posterior? Just like, because I don't really understand.
Okay, Paul, did you have a related question to that?
I had a separate question.
Okay, so let me address that one first. Okay, so back to this. Again, we're thinking about this as a prior predictive distribution, a representation of our prior predictive distribution, which is to say our model for the data before we observe the data. So if we were going to do this, we would choose M and S for all of those. I'm saying the default is the means for those normal priors is 0, and the standard deviation is 2.5 in standardized units. So whatever those M and S are, we draw 4 separate times from those normal distributions to get 1 beta 1, 1 beta 2, 1 beta 3, and 1 alpha. All right? Good so far?
Yeah. So just you put everything together and you have a Poisson.
Right. So you put all this together, you get eta for each of your observations, because these predictors vary. You exp eta to get mu. Also, eta has the logarithm of lambda in it. So We drew phi from an exponential distribution. For each observation, we draw lambda from the gamma distribution that has both shape and rate equal to phi. Then we take the logarithm of lambda, and that goes into eta as well. And then we exp eta to get mu, so you can also think of mu as being scaled up by lambda. Anyway, we draw, we get all those together, we get mu, and then we draw our prediction for the number of roaches caught from a Poisson distribution that has expectation mu sub n, where little n indexes the observations that we have from the buildings.
This is the prior.
Right, this is the prior predictive distribution. So it ultimately ends when we have simulations of the outcome.
And what is the distribution of the likelihood then?
So when we go to estimate it, it's more computationally efficient to integrate out the lambdas, which can be done analytically, in which case the likelihood is going to be negative binomial, but considered as a function of the parameters rather than the outcome. That can be done analytically. So there won't be estimates of the lambdas, because those got integrated out. There will be an estimate of the phi, in addition to the alpha and the betas and all that. Follow-up question?
I was wondering, why do we actually have mu equal to the Euler's number exponentiated to eta of n? Is it because just, it's the exponential growth of the roaches, or?
It's mostly to ensure that mu is positive.
Ah.
Sufficiently negative values of the coefficients, we could get an eta that's negative, in which case there would be an error message if we tried to use a negative binomial or a Poisson likelihood with a negative parameter. So we do the transformation to make it positive.
You go to the next slide. I had two small questions. So when you say offset equals log of exposure 2, what is exposure 2?
Exposure 2 is a variable in the Roach's data set that pertains to the number of days that the experiment went on, or something like that.
Okay, all right.
So you think the longer it goes, the more roaches you would trap.
And the other thing is that you said a one unit change in x, or 1 unit change in the standardized x corresponds to less than 5 unit change in the standardized y. I think you said that.
Eta, yeah.
Where did you get the 5 from?
So the default prior, because I didn't change it, the default prior in RStanArm for these generalized linear models is normal with an expectation of 0 and a standard deviation of 2.5 interpreted in standardized units. And so what I'm saying is if I switch senior variable from like 0 to 1, I'm anticipating with all probability that the change on eta will be less than 5 standardized units.
Okay.
Okay. Anyway, we estimate that. Certainly the posterior median of the past roaches is positive. Posterior median of the treatment variable is negative, or this is the main effect of it. So if that were 0, which doesn't exactly make sense. And then the interaction seems to have a positive median, but there's a lot more uncertainty about that interaction relative to the center of the distribution. That's that. This reciprocal dispersion pertains to phi. The fact that it is not infinity tells us that we're not in the special case of the Poisson. And that's about all there is to that. As usual, like all these coefficients pertain to the eta, so the log of the expectation of the number of roaches caught, and are not that suitable for interpretation, particularly with the interaction term in there. And also, for those of you who are really curious about that, it does seem as if being in a senior assisted building has a negative median, but we have a lot of uncertainty relative to that, probably because there's not that many such buildings. So how do we, have a single sort of conclusion about what is the estimated average treatment effect of this roach trapping device or whatever. So I create myself a new data frame, and then I'm allowed to investigate what does my model say would happen under various counterfactuals. So I make a copy of my data frame roaches, and then I just set treatment to be 0 for everybody. Calculate posterior linpred. This is going to give me the posterior distribution of mu if every building were under control group. We get essentially posterior distribution of the potential outcome under control. Call that Y0. Then go back into my copy data frame, make treatment equal to 1 for all buildings. Get the posterior distribution of mu under that assumption. And we can call that the potential outcome function under treatment. And then if I want to say something about the average treatment effect, I can subtract Y0 from Y1. Both Y0 and Y1 are going to be 4,000 by n matrices. And so I can take, or maybe they're transposed the other way. Anyway, I can average those over observations to get a posterior distribution of the average treatment effect, and then I can plot the density of that. And so there's a little probability of extremely large effects, almost no, but maybe some probability that the treatment actually causes more roaches. But certainly the bulk of this distribution would suggest that there is a negative effect on roaches. And you can calculate the median or the mean, whatever of that distribution, but it seems to have a mode of like -12 or something like that. Mm-hmm.
So actually, so what does that mean that the treatment is negative for the roaches? So like it works, or?
I think it means, yeah, it works. So I might have said it wrong. Roaches could be the number of roaches observed after the experiment rather than the number of roaches trapped. But the treatment was intended to have fewer roaches rather than more. I'm pretty sure of that. Anyway, so either way, this is the way you calculate in the Bayesian world your sort of distribution of estimates of the average treatment effect. Evaluate the implication of your whole model under whatever counterfactuals you want. And you can put this in the potential outcomes framework, or you can just think about it as estimating the average difference between roach prevalence under treatment and under control. Questions about that?
Can you help me think through this, like in the potential outcomes framework? Because I'm thinking, right, so when we're sort of like imputing or putting in the posterior distribution of mu if every building were under the control group, that's just like based on our estimates, right? But it's like we're still observing only like half of them or however many we assign, but we're just saying like based on the ones that we did observe, we're taking like the other like covariates of the buildings and like thinking about what would have happened had we not done the treatment. Okay.
So, fundamental rule of the potential outcomes framework, you only observe at most one of the two potential outcomes. But under a model, you can actually estimate the other potential outcome function. And we usually estimate both potential outcome functions and then take the difference rather than estimating one of them and subtracting it from the observed. That way it takes into account our uncertainty better. So yes, only one potential outcome is observable. Both or all, whatever, potential outcome functions are queryable from a model of the data generating process. And so kind of the reason why you can only observe one potential outcome function is you can only observe a building under control or under treatment. I guess this is not literally at the same time, but in my sort of counterfactual world, I can make all buildings treatment and then in the next instant make them all control and just query the model. So these are estimated potential outcome functions. These are beliefs about what the potential outcome functions are. And it's certainly true that a lot of people who favor experiments don't like to make too much modeling assumptions. But if you're willing to make the modeling assumptions, then the model sort of overcomes for you the fact that some of these are unobservable. Okay, flipping over. So if you have your computers, you should install ShinyStan from GitHub. There's another version that's in like alpha quality. It's actually better than that, but anyway, it's not on CRAN yet, and I will show how to do this in R. So if you call launch ShinyStan on an object created by Stan GLM or Stan LM, something like that, it will open up a web app. This is called ShinyStan. It was originally and mostly created by Jonah Gabry for his QMSS thesis when he was a QMSS student in like 2014, 2015, something like that. And it provides a way for you to understand more about posterior distribution that you generated. So this looks like the old version, but it's basically the same thing. So this one doesn't have any problems to diagnose. We'll see some ones later that do. You could look at the autocorrelation. So if you go into here, you can sort of click on the coefficient that you want, and then you can see the autocorrelation of the Markov chain. In this case, there's 4 Markov chains that get run simultaneously. You can see the negative first order correlation that I was talking about, which tends to give you effective sample size larger than the nominal sample size if this is negative enough to offset all the subsequent lags, which may be positive. So anyway, that's nice and all. You can also look at I need to scroll up. You can look at the effective sample size relative to the number of iterations. All of these are good. Like I said, there's no real problems with this particular model, so there's not a whole lot I can show you in terms of the diagnostics of that. If you go to the Estimate tab, then you can get plots of the posterior distribution for each of these. And so basically all of these are really precisely estimated except for the mean posterior distribution. So you can put a regular expression to get rid of that one. No, I'm not good at regular expressions. Okay, let's just do treatment and the interaction and all right, let's just look at one of them. In general, you can look at more than one at the same time. Anyway, you get posterior intervals. This blue dot is the posterior median. I think the red line is like a 90% posterior interval. This is on the interaction, so it's a very high chance under the posterior distribution that this is positive. But anyway, we don't have to dwell too much on that. If you need to make a table, you can get the summary statistics and you can choose whichever columns you want to have on that. You can also generate the tech for that if you need to paste it into R Markdown, some things like that. The alpha version of ShinyStan will also let you download these things as a report in PDF or R Markdown, or also these plots that you can make. You can get RDS file that has the plots in it. So more things you can click on and explore. I think they got rid of the trivariate one, which is unfortunate because it's my favorite. This you get sort of this three-dimensional view of the posterior distribution in terms of the coefficient on the treatment variable, the coefficient on past roaches, and the value of the posterior kernel on the vertical axis here. So, wait, get bigger. No, that's smaller. I said bigger. How does this work under Windows? On Linux, it just listens to me. Okay, well, that's just going to have to be small. Okay, so there's a glossary that defines all of these terms that you might encounter, and also links where you can go to get help. So this is already a pretty useful thing. And it's very useful for diagnosing problems. It's just there were no problems to diagnose in this particular example. So we'll come back to that when we actually have a model that starts to misbehave. But also the one on GitHub, the alpha version, this looks like it's the old version, is even better than this in terms of the number of things that you can do. But it's pretty self-explanatory for just like the number of things that you can click around. And where it's not self-explanatory, it has pretty good descriptions of what all these things are. One thing that I will call your attention to, because we'll start to see it for the reading on next week, is where are my lines? Okay, here's something I can look at. These posterior predictive checks. So if you sort of get the posterior distribution, draw from the posterior predictive distribution, how closely does that correspond to the observed data? When you see differences, that might give you reason to question the model or to question the data. And so we'll see more examples of that next week. So here what we have is sort of the average of the posterior predictive distribution along the horizontal axis and the observed number of roaches, I guess, along the vertical axis. And so there does seem to be a pretty linear relationship between those two things, indicating for most buildings, our model seems to be pretty well. But there's a few that depart from the line, and then there's one out here with like 25,000 predicted roaches, that it seems as if maybe that data point were wrong, or maybe our model is doing a terrible job in that building for some reason. Anyway, those are the sorts of things that you can look at when you have a model you can query as to what it would predict about things. And then to exit, you can just close out of that. Okay, so that's ShinyStan. And you fire that up by calling launch ShinyStan on an object created by something in RStanArm. It works for a bunch of different functions. So logit model. There's a lot of examples on this in the reading. I just wanted to sort of show in code how we would draw from a prior predictive distribution of a logit model when the outcome variable is either 0 or 1. 1 indicating success, 0 indicating failure in some sense. So the predictors in a regression model are not being modeled. They could be anything. So here I just have a hypothetical predictor that ranges from -20 to 20. Could be anything as long as it has a mean of 0. And if it doesn't have a mean of 0, you can subtract the mean so that it does. Remember, we like to center our predictors, and so we can interpret the intercept in a generalized linear model as the expectation of eta for a unit of observation that has average values of the predictors. So going through, you can do this 4,000 or 10,000 times, whatever it is, draw intercept, let's say from a normal prior. Usually with logit models, those are going to have lower prior standard deviations than for Poisson or for linear regression models, just because there's a limited range for eta. And if you go beyond that, when you do the transformation, the probability comes out to be essentially 1 or essentially 0 if it gets to be like more than a 2-digit number. We draw beta from standard normal prior, something like that would be fine. We create eta by multiplying beta by our predictor and then shifting over by alpha. And then we can draw an error term epsilon from a logistic distribution, in particular a standard logistic distribution. So this what makes it a logit model as opposed to a probit model. If we want to do a probit model, this would be drawing the error term from a standard normal distribution, or we could use Cauchy or whatever. But here we're using logistic, which is similar to the standard normal, but it has somewhat heavier tails. And so we have eta, which is our linear predictor. We have epsilon, which is this error term. Add eta and epsilon together to create, assuming the observations are individuals, the predicted under the model difference in utility between whatever corresponds to the outcome of 1 and whatever corresponds to the outcome of 0. So we add those two things together, and under our model, the model implies that we're going to observe the person make the choice for y equal 1 if the utility difference between y equal 1 and y equal 0 is positive for them. If utility is negative, that means they're getting more utility from whatever y equals 0 is than what y equal 1 is. And so when utility is negative, the model implies that y is going to be 0. And then we just spit back y. So there was a question on CampusWire of formulation of model in terms of latent variables. Here, utility is the latent variable. And so we're saying our model implies people who have more utility for the y equal 1 are going to choose that, and people who have less utility for y equal 1 than they do for y equal 0 will choose y equal 0. And it would be the same even if we were using a normal distribution for the errors and whatnot.
Is the utility here, is it like the treatment, which we specified to be 0 and then 1, the previous model that we subtracted the 2? So that's what's happening here with the y?
It's not. It's just sort of an intermediate variable. So we don't observe utility, but it's more like the potential outcome functions, actually, that I was talking about before. It's something that's fundamentally unobservable, but it's something that can be implied by a model. And so when we're drawing from the prior predictive distribution of the observable y's, we can formulate it to be depending on this unobservable utility. This makes a little bit more sense when the outcome variable is sort of explicitly a choice, like who would you prefer to vote for, something like that. But it's not something that we directly manipulate. If we wanted to do counterfactuals, we would say, well, what if the person's x were 1 instead of 0, or 20 instead of 10, something like that. And so then we can investigate the properties of our prior predictive distribution under this, and based on this prior for the intercept and the mean, all of the average probabilities come out to be pretty close to 0.5 as to whether they would favor y1 or y0. Question?
Treatment and no treatment. What would you like? Imagine like alpha is the effect of the treatment. Would you remove like alpha and that would be the distribution, and don't like we did nothing, and then have the distribution with alpha and then compare the two distributions?
Add a treatment variable. You can, if it's binary, you could think about, okay, just leave out that parameter from the linear predictor. But actually, when we do it, we multiply it by 0 or multiply it by 1, which yields the same thing. But the way that I was formulating it before, like with the roaches, and I just like set treatment to 0 and then counterfactual, and I set treatment to 1 and counterfactual. This way works under more general circumstances, like non-binary treatment variables or counterfactuals that involve like multiple variables simultaneously, things like that. So this is the kind of general way that always works, but the what scenario that you suggested would be equivalent to this. Okay. All right, we got a prior predictive distribution. And then, so what's the log likelihood for a logit model? So often there's like, there should be some connection between the process that you imagine for the prior predictive distribution and the way in which you estimate it. But it's not always like a one-to-one correspondence thing, particularly when you, in a logit model, introduce these utility variables governing the choices. So what's the Bernoulli probability mass function? And what's its logarithm? Got to learn the probability distributions.
0 and 1.
Right, so that's the sample space. Omega is either 0 or 1. The probability mass function is mu raised to the power of y times 1 minus mu raised to the power of 1 minus y, where mu is the expectation of the outcome, in other words, the probability. And then we can take the logarithm of that. Okay, so that's not so bad. Then what's the conditional distribution of utility under our logit model? So if epsilon has a location of 0, then utility is going to have a logistic distribution with a location of eta and a scale of 1. So the logistic distribution is also in the scale location family. And then what's the expression for the probability that y equal 1 if utility is logistic with expectation eta and scale 1? So that would be, okay, what's the probability that y is equal to 1? Well, that's the probability that eta plus epsilon is greater than 0, which can be represented under the logistic distribution, because the logistic distribution, like the normal, is symmetric. So this is a complementary CDF, but it's equivalent to the CDF of the logistic distribution, standard logistic distribution on eta, which is just 1 divided by 1 plus e to the negative eta. So that is the probability of success under a logit model. And then if you combine those things into your expression for the contribution of one observation to the log likelihood, you get an expression like this. If y equal 1, then we have this term, and if y is equal to 0, then we have 1 minus y multiplied by that term there. Anyway, all these are all built into Stan, and they're built into R. So you can just call like binomial LPD PMF, but this is sort of the math behind those things. So another example that I want to go through, this is for a poll that was taken like the night before the 2012 election between Obama and Romney. It was a poll done by Google. So that data set is on Canvas. It's kind of one of the rare scenarios in which you can actually get the individual level data on a poll. So want to win is the main outcome variable, and it's coded as 1 if the person wants Romney to win, and 0 if they want Obama to win. When all of your variables are categorical factors, it can be much faster in Stan and other programs as well. If you collapse them and use the binomial likelihood rather than the Bernoulli likelihood, because the intersection of all these categorical variables under your model is going to have the same probability of success, and we can add up all those underlying Bernoulli random variables to get a binomial random variable, but that is going to have a data set with much fewer rows, and it's just going to have the count of the number of people that fell into that category. So this is fairly easy to do with dplyr. I throw away some of the NAs, all the NAs I guess, then group it, the data frame by region, by gender, by urban density, like whether you live in a city, suburban area, or rural area, age category, income category of the person, and then summarize it by the sum of the number of people who say they want Romney to win, and obviously Obama would be n minus the number of people who want Romney to win in that category. And now we have a collapsed data set that is much faster to work with in Stan GLM. So we can use the same Stan GLM that we used for the negative binomial model before for this binomial model for the predicted outcomes, just by changing family from like neg binomial to binomial. And also, this is already the default, so I didn't have to specify it, but here I'm saying use the logistic inverse link function to estimate a logit model. That could have been probit, in which case the likelihood is still binomial. It just has a different assumed distribution for the error. When estimating a binomial model, you need to give it a combined outcome variable that is the number of people, you know, favoring Romney, favoring Obama in that category. Then, you know, I do this with the default prior, so I specify QR equal true, get back this summary of the posterior distribution. So we have, you know, for example, the posterior median for people who live in the South is quite positive in its posterior median relative to the posterior standard deviation, and that indicates what everyone who knows about American politics knows, that in the South there's considerable tendency to favor Republican candidates, at least for national office, you know, whatever. You know, men were more likely to support Romney, etc. And then you can see for the other ones. So here you might be maybe a little bit surprised that the posterior standard deviation on the category, the highest category of income, was so large relative to the posterior median there, but that is mostly because there were only a few people who had reported, you know, that much income in the sample. There's like 8 people or something like that. So it wasn't possible under this model and these priors to estimate that too precisely. But, you know, for lots of other reasons, we might suspect that people who have like, well, that's way less than Mitt Romney income. But if you had Mitt Romney income, you might very well favor Romney for president.
Could you explain again, like, why the median is negative? Like, what does that mean? Like, if it's supposed to be 0 for Obama, but the median is negative, like they wanted Obama to be elected so badly that the median is actually in the negative, or?
So well, let me find a negative. Yeah, so urban. That has a, you know, posterior median that's very negative, and so relative to the reference category, which I guess is rural people, people who live in cities were much more favorable towards Obama than they were toward Romney. Remember that this is coded that like the outcome variable is 1 means the person wants Romney to win, and at 0 they want Obama to win. So this being urban, you know, much more likely than a rural person to favor Obama in that election. Okay. So I went a little bit or way overboard on this plot, but I just wanted to show you like all the things that could be done with the Tidy Bayes package, which basically implements the combination of the sort of tidy approach to everything along with ggplot in order to make a plot that shows like everything simultaneously, which is not great, but just that's the code. You could take some pieces of it and make a more reasonable plot showing how the probability of someone favoring Romney varies like according to income and by age category, and there's different colors for the regions, and then men and women, whatever. Anyway, so you can make plots like this or plots much simpler than this to convey your point. And it's usually better to do that in graphs, particularly because like these raw coefficients they pertain to eta, not to the probability. You have to do the transformation, but that's implied by your model. So really just query your model and you can get this monstrosity of a plot or something more reasonable. So here I took like the default priors for everything. It turned out to be not that bad. This is not only a rare data set where you could get the individual data, it has like 6,000 observations, which is pretty big for a poll. So we were able to estimate a lot of things reasonably precisely, not that last income, but other things. But anyway, if you wanted to go through coefficient by coefficient, there's probably 20 of them here, and try to choose a prior. Maybe if you had like an hour, you could probably come up with something reasonable for each of those. But that's certainly pretty tedious. Another option that I favor is these R-squared priors. So in order to do that, you have to call the stan_POLR function, which is more intended for categorical ordered outcome variables. But if you just have two outcome categories, then you can consider them to be ordered in whatever order you want, since there's just two of them. So you can do essentially the same model, but stan_POLR supports the R-squared prior. This is a little bit different from what we were doing the other day on Tuesday, because you're basically saying how much, what percentage of the variation in utility do you think can be explained by a model like this? Because the observed outcomes are just 0 and 1, so there's that's discrete. There's no, it's not as meaningful to talk about R-squared on that quantity. So what this is saying is how much of the variation in utility for the two candidates and the difference thereof do you think can be explained by your model? And you always want to go pretty low on that in the social science. We think of politics, particularly close to an election, as being pretty predictable, but that's sort of aggregating over groups. At the individual level, even if we know a lot of the characteristics about you, it's not so precise to predict like this person is going to favor this or that candidate, particularly in this data set because it didn't ask about the race of the respondent. That would have helped a lot in any election involving Obama to explain why some people favor Obama and some people favored whoever Obama was running against. But anyway, you can do this. It's just R-squared for binary outcomes, particularly when they involve like political or social issues, tend to be a lot lower than like diamond price R-squared. But anyway, you get almost the same coefficients, and in my opinion, a simpler way to specify that prior. So you can also use the stan_GLM function to estimate linear models if you specify family equal Gaussian, which is the default. And so this is what is done a lot in the reading, particularly the reading for Tuesday, because stan_GLM allows you to put priors on the individual coefficients rather than on the R-squared. And in some circumstances, that may make more sense. The reading in the book the reading is taken from has a ton of examples where there's just like one, maybe two predictors. And in my opinion, those models tend to be too simple compared to the research models that people who are doing research in the social science want to estimate. And so if you only have one or two predictors, it's easy enough to think about priors on like a couple coefficients, maybe their interaction. But if you had, like 20 or something like that coefficients that you needed to think about simultaneously, then you kind of a lot of times have to switch over to thinking about some aspect of your prior on the coefficients collectively rather than individually. So like how much can all of these variables explain the difference in utility for presidential candidates. But this model for a data set where they give IQ tests to babies and then model the baby's IQ as a function of characteristics of its mother. In this case, we're just using the IQ of the mother and whether she graduated from high school and the interactions among those, between those. And so, that's all fine. This is an example where you probably should be able to specify prior intercept, remembering again that all of these are going to be centered. So your intercept, the prior pertains to what you expect the outcome to be for someone who has average values of the predictors. And IQ tests are like scaled and measured so that the average is 100. And so you have a pretty solid, if you just know about the construction of the test, being able to put a normal with an expectation of 100 and a standard deviation of 15. IQ tests are also constructed to have a standard deviation of 15 over the population. So in this case, you could use what you know about the test in order to make an informative prior, and then just put kind of like uninformative or weakly informative priors on the coefficients. You might think there should be a positive association between, the IQ of the mother, the IQ of the baby, whether the mom graduated high school, and to some extent that is true. But we don't have time to really go through this example fully. But if we did, you would sort of come to the conclusion that you cannot tell a whole lot about a baby from its mother, which is good for the baby in most circumstances. There's slight relationships along these lines, but it's sort of mostly noise. And that might be what you would expect if you tried to give an IQ test to a 2-year-old or something like that. Anyway, okay, out of time for today. I will post the homework tonight. It'll be due Thursday on RStanArm and stuff. And next week we'll continue learning more things that we can do with the output from a model estimated by the RStanArm package.